Testing industrial equipment designed for 400 volts 3-phase at 50 Hz and up to 250 amps requires careful planning and execution. Several methods can be used to achieve this, each with its own advantages and disadvantages. Firstly, consider transformers. A transformer can convert the available 208 volts or 480 volts 60 Hz power to 400 volts at 50 Hz. However, frequency-dependent effects such as core saturation, eddy currents, and winding impedance must be carefully considered. Custom-designed transformers with special laminations and winding techniques can be used to minimize these effects. Secondly, look at variable frequency drives or VFD. The VFD can convert 60 Hz power to 50 Hz power while maintaining voltage and current levels. This solution provides precise frequency control and can simulate realistic load conditions. However, VFD can introduce harmonics and other power quality issues which must be accounted for. Thirdly, there's the generator with speed control. A generator connected to a prime mover such as a diesel engine can be operated at a reduced speed to generate 50 Hz power. This method provides a clean and reliable power source with minimal harmonics. However, the generator and prime mover must be properly sized and designed for the required output. Fourthly, power converters. Advanced power converters, such as solid-state transformers or bidirectional converters, can provide highly precise and efficient voltage and frequency conversion. These devices are typically more expensive but offer several advantages, including power factor correction, harmonic filtering, and transient protection. Fifthly, simulation systems. Dedicated simulation systems designed for testing industrial machinery can provide a comprehensive solution. These systems typically incorporate multiple power sources, load banks, and monitoring equipment to create realistic load conditions and precisely control voltage, frequency, and other parameters. The most appropriate solution depends on the specific requirements and budget constraints. For high current loads and precise frequency control, a VFD or generator with speed control is recommended. If power quality and efficiency are critical, a power converter or simulation system may be the optimal choice. In addition, determine the actual load profile of the machinery to ensure proper sizing of the power source. Consider the operating environment, such as temperature, humidity, and altitude, which can affect power generation and system performance. Adhere to all applicable safety standards and regulations for electrical installations and testing procedures. Now let's delve into each of these options with more detail. When using a transformer, it's vital to understand the potential problems arising from operating a transformer at a frequency different from its design frequency. A transformer designed for 60 Hz operation, if used at 50 Hz, will experience increased core flux density. This is because the voltage to frequency ratio is a key factor in determining the core flux. If the voltage is held constant while the frequency is reduced, the core flux increases. Excessive core flux leads to saturation of the core, causing several undesirable effects. Firstly, increased magnetizing current. As the core saturates, the magnetizing current increases dramatically. This can lead to overheating of the transformer windings and reduced efficiency. Secondly, harmonic distortion. Core saturation introduces harmonic currents into the system, which can negatively affect power quality and interfere with other equipment connected to the same grid. Thirdly, reduced voltage regulation. The increased magnetizing current and harmonic distortion can worsen the transformer's voltage regulation, causing voltage drops under load. To mitigate these issues, you might consider using a custom-designed transformer. Such a transformer could be designed with a larger core specifically intended for 50 Hz operation. The larger core reduces the flux density and minimizes saturation effects. Using special core materials such as amorphous steel or high-grade silicon steel can also reduce core losses and improve efficiency at 50 Hz. Also, employing advanced winding techniques can minimize leakage inductance and improve voltage regulation. Another alternative is to simply derate the existing 60 Hz transformer. If using an existing 60 Hz transformer, it should be derated to avoid overloading and overheating. The derating factor depends on the transformer design, but typically ranges from 15 to 20%. Next, consider variable frequency drives. VFD provide a flexible solution by converting the incoming 60 Hz alternating current power to direct current, and then inverting it back to alternating current at the desired 50 Hz frequency. The voltage and frequency can be precisely controlled, allowing for simulation of various operating conditions. With VFD, you can easily adjust the voltage and frequency to match the specific requirements of the equipment under test. This is particularly useful for testing equipment under various load conditions and simulating real-world scenarios. You also gain the ability to soft start and stop the equipment under test. This reduces mechanical stress and extends the lifespan of the equipment. VFD often include built-in protection features such as overcurrent, overvoltage, and undervoltage protection, which can safeguard the equipment under test and the testing infrastructure. But as stated before, VFD can introduce harmonics into the power system. These harmonics can cause interference with other equipment, increase losses in transformers and conductors, and potentially damage sensitive electronic devices. To mitigate harmonics, several techniques can be employed. Firstly, use harmonic filters. These filters are designed to block specific harmonic frequencies, preventing them from propagating through the power system. Secondly, implement multi-pulse VFD. Multi-pulse VFD use phase-shifting transformers to reduce the harmonic content of the output current. Thirdly, employ active front-end VFD. Active front-end VFD use active components to control the input current waveform, minimizing harmonic distortion. When selecting a VFD, it is crucial to choose one that is appropriately sized for the load. An undersized VFD may not be able to handle the required current, leading to overheating and failure. An oversized VFD may operate inefficiently and cost more than necessary. Consider a generator with speed control. A generator driven by a prime mover such as a diesel engine or electric motor can provide a clean and reliable source of 50 Hz power. By controlling the speed of the prime mover, the output frequency of the generator can be precisely adjusted to 50 Hz. Generators offer several advantages. Firstly, they provide electrical isolation, which protects the equipment under test from disturbances on the main power grid. Secondly, generators produce a clean sinusoidal waveform with minimal harmonic distortion. Thirdly, generators are self-contained and can operate independently of the grid, which is useful in situations where grid power is unreliable or unavailable. The size of the generator must be carefully matched to the load requirements. An undersized generator may not be able to supply the required power, leading to voltage drops and potential damage to the equipment under test. An oversized generator will operate inefficiently and waste fuel. Ensure that the prime mover is capable of maintaining a stable speed under varying load conditions. Fluctuations in speed will result in frequency variations, which can affect the accuracy of the test result. Also, generators require regular maintenance, including oil changes, filter replacements, and spark plug replacements. Neglecting maintenance can lead to reduced performance and premature failure. Power converters, also called solid-state power converters, offer a highly flexible and efficient solution for voltage and frequency conversion. These devices use semiconductor switches to convert alternating current power to direct current, and then invert it back to alternating current at the desired voltage and frequency. Solid-state power converters offer several advantages. Firstly, precise control. They provide precise control over voltage, frequency, and phase angle. Secondly, bidirectional power flow. Some converters allow for bidirectional power flow, which can be useful for regenerative testing. Thirdly, power quality improvement. They can improve power quality by filtering harmonics and correcting power factor. Solid-state transformers replace the traditional transformer with a combination of power electronic converters and a high-frequency transformer. This allows for more precise control over voltage and frequency, as well as improved efficiency and reduced size. Bidirectional converters allow power to flow in both directions, which is useful for testing equipment that can generate power, such as electric vehicle chargers. When selecting a power converter, ensure that it meets the required voltage, current, and frequency specifications. It must also be capable of handling the load profile of the equipment under test. Power converters generate heat, which must be dissipated to prevent overheating. Ensure that the converter has adequate cooling and ventilation. Also, power converters can be complex devices requiring specialized knowledge to operate and maintain. Ensure that qualified personnel are available to support the testing process. Simulation systems provide a comprehensive solution for testing industrial machinery. These systems typically include multiple power sources, load banks, and monitoring equipment, all integrated into a single platform. Simulation systems allow for the creation of realistic load conditions, which can be used to thoroughly test the performance of the equipment under test. They offer precise control over voltage, frequency, and other parameters, allowing for the simulation of various operating scenarios. Simulation systems typically include data acquisition and analysis tools, which allow for detailed monitoring and analysis of the equipment under test. Simulation systems can be expensive to purchase and maintain. Ensure that the benefits justify the costs. These systems can be complex to operate, requiring specialized training. Ensure that qualified personnel are available to operate the system and interpret the results. Also, ensure that the simulation system is properly calibrated to ensure accurate results. Regardless of the method chosen, several additional considerations are important. Understanding the load profile of the equipment under test is crucial for selecting the appropriate power source and ensuring that it is properly sized. The load profile includes the voltage, current, power factor, and harmonic content of the load, as well as any transient conditions. Ensure that the power source can handle the maximum demand of the equipment under test, as well as any short-term overloads. Consider the environmental conditions in which the testing will be conducted. Temperature, humidity, and altitude can all affect the performance of the power source and the equipment under test. Ensure that the power source is rated for the operating environment and that adequate cooling and ventilation are provided. Adhere to all applicable safety standards and regulations for electrical installations and testing procedures. This includes ensuring that all equipment is properly grounded, that appropriate safety interlocks are in place, and the qualified personnel are performing the testing. Before commencing testing, develop a detailed test plan that outlines the objectives of the test, the procedures to be followed, and the acceptance criteria. This will help to ensure that the testing is conducted in a systematic and consistent manner and that the results are reliable. Ensure that all test equipment is properly calibrated before use. This includes voltage and current meters, frequency counters, and power analyzers. Calibrated equipment is essential for obtaining accurate and reliable test results. Implement a robust data acquisition system to capture all relevant test data. This includes voltage, current, frequency, power factor, and harmonic content. The data should be stored in a format that can be easily analyzed and interpreted. After completing the testing, thoroughly analyze the data to determine whether the equipment under test meets the acceptance criteria. Document the results in a comprehensive test report that includes a description of the test setup, the procedures followed, the data acquired, and the conclusions reached. Finally, consider the long-term costs associated with each solution, including purchase price, installation costs, operating costs, and maintenance costs. Choose the solution that provides the best value over the lifespan of the equipment. By carefully considering these factors, you can select the most appropriate method for testing industrial equipment at 400 volts 3-phase 50 Hz and ensure that the testing is conducted safely and effectively. This will help you to verify the performance of the equipment, identify any potential problems, and ensure that it meets the required standards.